Great, we are ready. Our first talk is from Weizhe, who is a final year PhD student in ECE at Cornell University, advised by Professor Aditya. His research focuses on improving both the efficiency and security of deep learning by co-developing algorithms and hardware architectural techniques. And as he said, he's the final year, maybe you are on the job market, so reach out to him. Feel free to start.
Thank you. Hello, everyone. Yeah, thanks, Chair, for the introduction. I'm Weizhe. Today, I'm more than excited to present our recent work on optimize the off-chip memory protection for data-intensive accelerators. This is a joint work with my colleague Umar, Professor Zhiru, Zhang, and my advisor Aditya from Cornell University. So in recent years, there are a lot of emerging applications that requires such as self-driving car, cancer diagnosis, and genomic alignment that are both data intensive and computer intensive. At the same time, performing those tasks require accessing sensitive and private user data. That means we need a computer system that can deliver both high performance and strong security guarantees. Hardware-based protection, which is also known as a trusted execution environment, such as Intel SGX, can offer higher performance than crypto-based solution. And recently, there's a line of research on specialized TE that are emerging for various hardware accelerators. For example, Microsoft Preview is confidential GPU VM for NVIDIA GPU. NVIDIA announced Bluefield DPU for secure autonomous driving, and Graphcom proposed TE extension for its AI accelerators. However, we found that for these accelerator TEs, the memory protection remain as the major source of overhead. And in this work, we proposed an application-specific memory protection scheme for accelerators named MGX, stands for Memory Guard for Accelerators. So our key observation is memory access patterns and granularities can be largely determined for a particular application. And given an accelerator application specific characteristics, we can customize the memory protection for those accelerators, which can significantly lower the protection overhead. And here are some of our key results. By applying MGX, we are able to reduce the average performance overhead for memory protection from 28% to 4% for DN accelerators and 33% to 5% for graph algorithms. We are also able to cut the worst case overhead from over 45% for some very intensive DN application to only 6%. And lastly, we found that MGX is also applicable to other critical applications such as H.264 video decoding and genomic alignment. So in our accelerator TE threat model, we assume that there is a secure accelerator which is trusted and cannot be probed or tampered with. There's an untrusted external memory, and this accelerator is going to read and write data from and to the external memory. So for confidentiality, the secure accelerator must write the encrypted data to the external memory. And for integrity, it must check if a memory read retains the most written value that was previously written by the secure accelerator. So before going to the details of MGX, let's do a quick recap on how memory protection is done in today's TE. So today's TE uses the AES counter mode, which requires a counter that is consistent of the physical address and the version number. So the version number is used to track the number of reads to the particular cache line. And after you do the encryption, you write the encrypted block to the off-chip memory, but at the same time, you also need to store the metadata, which is the version number, to the off-chip memory, because you will need this version number when you decrypt the data. Because the CPU can have any arbitrary memory access pattern, that means for each cache line, you need a dedicated version number, right? Because you don't know what's the version number for this cache line or that cache line. So you need a dedicated cache line. So we end up with having many version number in the off-chip memory. And what makes it even worse is that to protect the integrity and also the freshness of the VNs, we also need to build a hash tree, or so-called Merkle tree, where on a memory read, you need to recursively verify the version number has not been tampered with. So for integrity protection verification, that's easier because you just have a MAC unit and you just compute a message authentication code for each cache line. So now we know where the overhead of memory protection comes from, right? So the first thing is to store per cache line metadata, in other words, VNs and MACs in the off-chip memory. And also we need to verify the VN recursively until reaching the on-chip root of the Merkle tree. You can do some optimization by caching all this metadata, but still a huge overhead. So now let's take a look at some real number of the overhead. The x-axis is a bunch of data-intensive applications running on accelerators. The y-axis is the memory traffic increase. And we found that for DN inference, the average memory traffic increase is over 36%. And for DN training, it's over 40% because DN training is going to be more data-intensive than DN inference. And for graph algorithms such as PageRank and also BFS is better than DN, but still over 25%. So in this sense, we propose MGX leveraging the high-level idea that data movements are often explicitly scheduled between the on-chip buffer and off-chip memory, and are also known for a given task. So in this specific example, if you just look at the ResNet and think about, we have a DN accelerator that has running this ResNet. So the memory access pattern of this accelerator is largely determined by the ResNet architecture, right? So you can also think this is a control data flow graph. So our key idea is that we can actually generate VNs for memory protection without using off-chip memory. And another observation we made is that data access in these data-intensive accelerators typically happen as a coarser granularity. Also, in this specific case, instead of just accessing one cache line at a time, the DN accelerator is going to access maybe the entire feature map at a time. So what we can do is we can have each MAC to protect a larger memory chunk, for example, the entire feature map. Okay, so now let me tell you some detail about our MGX scheme. The first part is version generation. So what we do is, let's try to keep some register in the on-chip, keep some on-chip register to keep track the status of the accelerator. And we use this as input to the control processor. And we let the control processor to generate the VN for memory reads and writes. Because we are able to generate the VN, there's no longer need to store the VN in the off-chip memory. And therefore, we can also eliminate the Merkle tree in the off-chip memory as well. For integrity verification, because we know that some of the cache blocks, they are grouped together, they will be accessed at the same time, they will have similar memory access pattern. So what we do is, instead of having calculate each individual MAC for each cache line, we just calculate one MAC for the entire large data block. And let me illustrate the idea of MGX. Use a simple example. This is a simple feed-forward network, and we assume that the feature maps of the network is written to the off-chip memory only once. And in this case, we only need to keep the layer ID in the accelerator state, in the sense that for memory reads, we just use the layer ID as the version number. And for memory writes, we just use the layer ID +1 as the layer ID as the version number. And like for a first layer, the VN number for read is 1 and the VN number for write is 2, and so on and so forth. So it's very simple. However, like in real life, DN accelerators are not that simple, right? Because we know that, for example, tiling is always used in DN accelerator. So let me first talk about what is tiling, right? Tiling computes a partition of output at a time due to the limited size of the on-chip memory. So in this case, as you can see, it first take a chunk of the input feature map and also compute a chunk of the output feature map. Then it compute over all spatial location to leverage the data reuse of the weight kernels. And then after it finish all the spatial location, it start to move onto the next set of input channel. And when you compute the next set of input channel, you have already have some partial results that's was generated from the previous round of the computation. So you just load this partial result back, update the partial result, and write them to DRAM again. So in this sense, we need to write the output feature map to the DRAM more than once. So for sure, MGX can handle this case. So now let me tell you how can we apply MGX for DN with tiling. So if the DN accelerator is equipped with tiling, then we just need to track a few more registers in the accelerator state, such as input tile ID, output tile ID, and the write memory counter. So given we have those registers on chip, we can just construct the VN in the following way. And like in this very simple example, and when we do the first tile, all the counters are 0, and we just construct the VN, and we move to the next spatial location, and we can just construct the VN in a similar fashion. And the interesting thing happened when we finish all the spatial location and move on to the next step of input channel. So at the time, you notice that we are not only reading the input feature, but also reading the previous partial results to the accelerator. As you can see, it's important that we will be able to reconstruct the counter or version number that was used to write the partial result. And finally, you just update the partial result and write it and update the write memory counter, because at the time you have already updated this partial result once. So you just increment the write memory counter and you just write this updated partial result to the object memory. In addition to DN, we also look at graph algorithms such as the PageRank, because people believe that, okay, PageRank, like graph algorithm, probably have more sophisticated memory access pattern than DN. So given so for PageRank, we first have a graph topology. We represent the graph topology in adjacency matrix, which is a sparse matrix. So for accessing this sparse matrix, you probably will have some irregular memory access, right? And for each vertex in the graph, you will have is associated with a feature, which is also in this case known as rank. And you just do a matrix vector product between the adjacency matrix and the rank. You get the updated rank, right? So this is how PageRank works. So the problem is now we have irregular access to adjacency matrix. So can we handle this? Yes, it's simple, because the adjacency matrix is read-only during the entire PageRank. So we only need a constant VN for this adjacency matrix. And how about the ranks? So we also observe that the updated rank from the previous iteration will be used as the rank in the next iteration. So it's also very trivial in the sense that we can just keep the iteration as part of the accelerator state to reconstruct the VN. Now let me talk about the experimental setup. For the performance simulation, we use the scale sim to simulate the DN accelerator, and we use the RTL simulation of a graph accelerator called Graph Lily to simulate graph algorithms. And for memory simulation, we use we build a cycle-level memory protection simulator combined with a RAM emulator. And for the protection baseline, we are modeled after the Intel ME white paper, which has the following spec. And we evaluate our scheme on a variety of DNs for vision and language tasks, and we also evaluate on graph algorithms such as BFS and PageRank on real-world large-scale graphs. So let me just show you some results on ML benchmarks. So the x-axis is a variety of deep neural networks, and the y-axis is execution time normalized to the baseline accelerator without protection. So for DN inference, the average overhead is 24%, and the maximum overhead is over 40% for this DRM, the Meta's recommendation model. And if we just apply the VN generation idea to the baseline protection, even without the cross-grain MAC, we are able to reduce the average overhead to 6% and limit the worst case overhead to 8%. And if we further add the cross-grain MAC into the scheme, which gives you the full-blown MGX, that will reduce the average overhead to 3% and the worst case overhead to 4%. So in summary, there are more in the paper. we talk about the detailed threat model and security analysis, and we give a detailed MGX scheme and experimental results for DNA and graph processing accelerator. We also discuss how can we apply MGX for other applications. And in conclusion, I want to highlight that MGX can provide near zero overhead memory protection for a wide range of data-intensive accelerators, and we truly believe that TE on accelerator with MGX is a promising solution to high performance and secure computation on private data. So this is the end to the end of the talk, and yeah, thanks for listening. I will be happy to take any question.
Thanks very much. So if you have any questions, feel free to come here.
Hello, Young-Suk Kim from Yonsei University. Thanks for the great talk. It seems that MGX is currently assuming a single data flow for a single DNN accelerator. But however, recent DNN accelerator proposals tend to implement multiple data flows. So in that case, even for a single convolutional layer, the memory access patterns from that single accelerator may differ a lot.
Yeah.
In that case, can MGX support such heterogeneous memory access patterns?
Yes, for sure. Like I would think, so we present, or I present MGX or illustrate MGX in a nutshell, right? It's for illustration purpose. Imagine that you have a very complex scheduling of the DNA accelerator. You have very complex data flow, but all those information are either like they're so for example, if you have a control processor, it will be compiled by the compiler and then as a kernel, and this kernel will be issued to the control processor. So the control processor know exactly the scheduling, right? So based on the exact scheduling, you can easily reconstruct or assign VN no matter how complex your access pattern is. Yeah, thank you. Thanks for the great question.
Yeah, I missed a crucial aspect of your talk. How did you avoid the need to keep the Merkle tree root in the TEE? That was one of the major points of your talk. I missed it. Could you re-explain? Yeah,
thanks for the great question. So essentially, the reason why we need a Merkle tree is because like the replay attack, right? You are worried about a VN will be replaced by a previous VN, and you will no longer not be able to detect that if you not have the tree and have the root of the tree on chip. So now the interesting thing is, what if we do not have VN at all in the off-chip memory? We do not keep any version of for the cache lines in the off-chip memory. Then what to protect? Nothing to protect, right? We don't need to protect the integrity and the freshness of the version number. So we no longer need the tree. Yeah.
Thanks for the talk and the questions. Let's give another round of applause. While Moni is setting it up, let me introduce our next speaker, which is with Moinuddin, professor from Georgia Tech. I don't think I really need an introduction here because all of you must have heard his experience during the launch. He got this award for his contributions to high-performance computing, high-performance memory system. And because this is security session, so you know that he's working on something different nowadays. Just as a junior faculty, I'm really impressed and curious how a senior professor could work in this way. And let's see from the talk. It's already there. Just click X. Okay, got it. And make it small. Make it minimalized. It's okay. Great. Great.
Thank you for the introduction, Mengjia. Research is fun, right? So solving problems is fun. This was a lot of fun. So I'll be presenting our work on Hydra, enabling low overhead mitigation of Rohan at ultra-low thresholds. This is a joint work with Aditya, Rohan, Gururaj, Saileshwar, and Prashant Nair. Prashant is at UBC. So we want more and more memory. The way we We want more and more memory. We try to pack cells. When the cells become closer, there is a little bit of leakage, and this leads to data interference. One of the most popular data interference attack is rowhammer. Here is shown a bank of rows, and if you keep activating some rows a lot, then the neighbors get bit flips, right, because of the leakage. And this phenomena is called rowhammer. It's a very popular phenomena, researched a lot. The rows that get a lot of activations are called aggressive rows. The rows that get the bit flips are called victim rows. And this is very easy to do. You can just use a flush instruction and just repeatedly access the same line again and again and again and bypass all of the caches. This is not just a reliability problem. There are several attacks that have used these bit flips to modify the page tables, take over the system, even read the data, right? So this is a serious security problem. And you might say, well, I know rowhammer, I've been hearing about it since 2014. Tell me something new. The problem is rowhammer is a moving target. The threshold in 2014 when it was demonstrated was 130,000 activations to cause a bit flip. It came down to 20,000. It came down to 10. Now, last year when it was characterized, it was at about 4.8K for current generations, right? So Owners Group has done a phenomenal work in characterizing this. If it has dropped 30x in the last 8 years, if we are developing solutions, should we target where we are now, or should we target 5 to 7 years from now at least, right? So the goal of this work is, yeah, we have rowhammer threshold of 5,000, but let's say I want to design something that's about 500 or lower. What do we need to do, right? So our goal is to tolerate rowhammer below 500. The typical way to tolerate rowhammer and something that's already a part of DDR4 is you track the aggressor rows somehow. When the count reaches a particular threshold, you issue a mitigating action, right? And the typical mitigating action is, well, let's refresh the neighbors of an aggressor row. That's very well understood. It's implemented. It's been beaten badly, right? So there are attacks like trespass, blacksmith. So this is a very popular thing to do. You break it and you become famous, right? So rowhammer attacks keep coming in. Now the thing is that the memory companies who implemented these trackers, they are quite intelligent, right? Why do these trackers keep breaking? Fundamentally, again, because this is a moving target. You have 64 milliseconds for a refresh. It takes about 45 nanoseconds to do one activation. Roughly, you can do 1.4 million activations in 64 milliseconds to a bank, right? What does this mean? Well, the number of rows that can be attacked is really a function of the threshold. If you can do 1.4 million activations, if the threshold was 100,000, you can only have 14 attack rows in a bank. 32 bank, 448 rows, no problem, right? Very small. 10,000, this number increases. 1,000, this number increases a lot, right? And this, if you already knew which rows are the attacker rows, you don't know that, right? When you start out, you don't know which of these rows are attacker rows. So as the thresholds reduce, the number of attack rows increase, the amount of hardware that's required increases. The companies don't really want to pay that much hardware. They cut corners, and then the attackers come in and figure out. So why don't we build better detectors? Well, this is a very good area of research. It's been going on for the last 7 years. People have built very nice SRAM-based detectors, right? Graphene is the state of the art. Twice, CAT, there is a Bloom filter-based detector. Most of these studies evaluate about 32,000 threshold. And I'm also showing naive, right? If you have one counter per row, you need roughly 4 megabytes. These solutions are really, really good. Where's 4 megabyte and where's 5 kilobyte, right? But 32,000 threshold is not really important. We want something that scales to lower threshold. At 250, your nice solution is 2 megabyte. Some of these trackers are even more than 2 megabyte. Right? So as your thresholds reduce, we don't really know how to track them efficiently. Right? SRAM-based trackers incur impractical overheads. And what we want to do is we really don't want to pay too much, right? We don't want to pay more than 64 kilobytes. So why 64 kilobytes is the size of the metadata cache with SGX. So, well, fine. I can't do SRAM-based tracking. Why don't we take all of the state, keep it in the DRAM array? You can have any number of trackers. The size of the tracker is 2 megabytes, which is not that big. You can put it in DRAM. But then every time you do an activation, you have to go and update those counters. Too much performance overhead. You put a cache, even if you have a 64 kilobyte cache, 128 kilobyte cache, 256 kilobyte cache, you still have about 25% slowdown. So we did this DRAM tracker work about in 2014. The scheme is called counter-based row activation. This is the slowdown. Even with very large caches, DRAM-based trackers are not that great. Right? They're secure. They don't require that much SRAM, debatable, but they have very high performance degradation. Ideally, what we want trackers that work at ultra-low threshold. We don't want to pay too much SRAM. We don't want too much performance overhead. And we really don't want to change the DRAM, right? Like, because that's a big no-no. The basic insight that makes our work, our solution possible is very simple. Row hammer is a time-bound problem, right? It's a race against time. You can attack a few rows many times. You can attack or access a large number of rows few times, but you just don't have enough time to attack millions of rows thousands of times. Right? And here is some characterization data. Like, I don't expect you to, this is not an eye test, right? This is some characterization. Basically, applications within 64 milliseconds tend to access roughly 100,000 or 300,000 rows, but the average activation count is very low, like 10. The number of really hot rows that receive more than 250 activation is actually very small, a couple of thousand. So you should have the ability to track all the rows, good for security. But when it comes to actually accessing the metadata, if there was just a good way to filter out most of the common case, that can enable a good solution. And that's really the insight. Why stick with SRAM only? Why stick with DRAM only? Why not have a hybrid that works, that has the best of both worlds? We propose Hydra, a hybrid tracker. It uses an SRAM filter for group tracking of activation counts. Group tracking of activation counts, right? And for most rows, that's fine. If you're accessed only a few times, group tracking is effective. You don't need anything else. If your row maps to a group that is heavily accessed, fine, then go access your particular entry from the DRAM and maybe cache it. Right? That's the basic idea. Use SRAM for group filtering. In cases where the row is really heavily accessed, fine, revert to DRAM-based tracking. Right? So let me give you a simple example. Let's say you want to track a threshold of 250, right? Hydra threshold of 250. Let's say, I will track for a group threshold to about 200. If the group has more than 200, I'll revert to per row tracking, right? So you access a row, you check the group count, it's less than 200, great. Don't need to do anything else, just increment the counter of that group count table. Oh, sorry, it's 200. Oh, that means this row requires per row tracking. Let me go and check the cache, the row count cache. Oh, it's there, good. I don't need to do anything else. I already have the counter plus plus, counter has reached the threshold, issue a mitigation. Sorry, it's not there in the cache. In that case, go, make a DRAM access, get your counter, put it in the cache, increment it, issue a mitigation if necessary. Fairly simple scheme. For our workloads, roughly 90% of the accesses just get filtered by the group count. You don't need to do anything else. The group count filter is about 32 kilobytes, 32K entries of 1 byte each. We have a 12K entry row count cache that filters the 9%, and only about 0.3% of the accesses need to go to DRAM. Right, so the tracking part is done, but rowhammer requires not just tracking within a window of 64 milliseconds. And so what do? Every 64 millisecond, reset the tracker state. How about the DRAM? Well, let's just reset the SRAM state. Because if the SRAM state is reset, even if the DRAM has garbage values, you're just not going to access the DRAM values, right? So good. Every 64 milliseconds, reset the SRAM state. When do you set the DRAM state? Well, When increment the group count from 199 to 200, you know that you are no longer going to be able to do group count. For all the rows that map to that group, go and set the values in the DRAM row count table to 200. So you must be wondering, well, how many rows do I have to update? How many memory accesses do I have to do? We use some intelligent indexing such that all of the rows that map to the GCT are placed in the contiguous cache lines, right? So for our design, roughly 128 rows map to the same GCT. That means you need 128 bytes, 2 cache lines, so it's just 2 read, 2 writes, not too much, right? And you might be thinking, well, what if I started accessing a row, but the group count was already 200? No problem. It's possible that the first time a mitigation gets issued at 50, but if you keep accessing, your counter is reset, you're using per row tracking, then a mitigation will only be issued at every 250, right? So it's possible the first one's at 50, but after that, it's 250, 250, 250, 250, just like a per row tracker. So the paper has security analysis. I said 250 for a reason. We actually wanted to target a threshold of 500. But whenever you reset the tracker state, you actually lose information. So if you want to track 500, you really need to design a tracker that works at 250. Regardless of your access pattern, this scheme is designed to issue a mitigation at least once every the Hydra threshold. In the paper, we have protection for RCT rows. And this is just a tracking mechanism. It doesn't say anything about what kind of mitigating action you can do. You can do blocking, you can do randomization. In the paper, we just evaluate refreshing 2 rows on either side. Right, so next results. We use an 8-core system, 32 gigabyte memory, 2 ranks, 8 kilobyte row buffer. This graph shows the normalized performance compared to a system that doesn't require any mitigation for graphene, which is a SRAM-based tracker. It requires a lot of storage at the memory controller. Second is CRA, which is the in-DRAM tracker. And third is Hydra, right? So graphene requires lots of SRAM. CRA requires lots of performance degradation. Hydra doesn't require Hydra doesn't induce a lot of slowdown. It requires about 0.7% slowdown, and it has very low SRAM overheads, right? And we did this study with DDR4, which is currently the popular memory standards, but maybe in the next year or so, DDR5 will take over. How does that matter? DDR5 will move from 16 banks per rank to 32 banks per rank. That means trackers that are at per bank, you'll need to double them. So what does this mean for the SRAM overhead? Here's the table for graphene, twice, CAT, and the Bloom filter-based scheme for DDR4 and DDR5. For DDR5, you're really in the megabyte, multi-megabyte regime, and companies like Intel and AMD, if you tell them, give me a megabyte to solve Rowhammer, they will say, we would much rather use that as a cache, right? But Hydra is scalable even for DDR5. It also needs DRAM, but the DRAM is really, really small. It's about 4 megabyte for 32 gigabytes, so it's like 0.01%, negligible. And so to conclude, Rowhammer is a moving target. The one critical part of Rowhammer is tracking aggressor rows. As you go to sub-1,000 thresholds, the amount of SRAM required for SRAM-based trackers is just impractical. If you just keep the state in DRAM, then accessing the tracker state incurs significant performance overhead, while live in the binary world of SRAM and DRAM, right? Have a hybrid tracker. SRAM, use SRAM for what it's good at, filtering, and DRAM for what it's good at, arbitrary tracking of any number of rows. Hydra requires very little slowdown and very little performance, very little SRAM overhead. Thank you, and I'll be happy to take any questions you may have.
Just curious in case I missed it. When you're launching Rowhammer on DRAM, why doesn't the cache hierarchy filter out the accesses going to DRAM?
It's a good question. The question is, when you launch Rowhammer, why doesn't the cache hierarchy filter out those accesses, right? So there are ways to circumvent the cache hierarchy. For example, use flush instruction. You bring the line, flush it. Second is use prime probe, right? So You have a 16-way cache, do a row hammer attack on 17 lines, just access them continuously, they'll just get that. And there you can do row hammer with non-cacheable loads.
Yeah, Peter Deutsch from MIT, great talk. I was just wondering if I put my attacker hat on and I want to, if the threshold to get to the row count cache is pretty low, could I as an adversary just thrash this cache and then incur some performance overheads?
That's correct, right? So remember that in any system, if you do sort of like badly access pattern, even for your LLC, you can get bad performance. So similarly, like if you want to get bad performance, you can get bad performance. But the important thing is it doesn't sacrifice security, right? If you come up with access pattern that like just goes through and then like fills a group and then prime probes the RCC, yes, you can get bad performance. But why go through all that, right? Just take your LLC, do prime probe, you'll get bad performance.
Okay, thank you.
Controversially from Telecom Pi, you kind of mentioned what my question will be about. Is Hydra does Hydra create a cache shaming attack vulnerability on the cache, on the counter cache, on the GCT, on the counter track, on the tracker cache? Because it will be possible to using an attacker can try to replace the most common line and trying to then attack using this pattern.
Yeah, so good question, right? So what about, we have a very nice way of tracking all of the state, but what if now I attack the rows that store the counters, right? So that's like the third bullet. That's in the paper. Basically, the counters for the rows that store the counters are stored in SRAM. It's about 500 bytes, right? Because you need 1 byte for 8 kilobytes, right? So it becomes very small. At that point, you don't want to even do recursive lookup, right? Take 500 bytes, just keep it in the memory controller, and that's what we do, right? The counters for the rows that store the counters are just kept in the memory controller. Yeah.
Hi, first of all, thank you for the amazing talk. I had a question. So the mitigation time definitely lies on the critical time of the program. However, since you are using a DRAM to track accesses of, say, groups, you also have a counter somewhere which is counting whether it is going above a threshold. And does this mean that every single access of the DRAM lies in the critical path of time?
Okay, so the group count is never kept inside the DRAM, right? The group count is an SRAM filter. You just look up, is it less than 200 or not? If it's less than 200, you're done. You just have to increment the counter, you're done. You never store that group count in the DRAM. In the DRAM, it's a per row state. That's only used if the group count is not enough, right?
Okay.
Yeah, I mean, even though the updating, like accessing the counters from DRAM is not in the critical path, but it's really the extra accesses that clog up the bandwidth and then creates contention. So the second order effect that comes to bite you. These counters can really be updated or even access off the critical path. But the moment you have a memory system that does more accesses, doesn't matter whether it's critical path or not. You just send more requests, you'll get more contention, and there will be degradation.
Okay, thank you.
Thanks for the great talk and all these questions. Let's give another round of applause and let's for the next one to step it up. Great. We have our last speaker, Sangpyo. He is currently a PhD student at Seoul National University, and he is advised by Professor Jung. His research interests are domain-specific accelerator, parallel computing, and privacy-preserving computing. Look forward to talk. Okay, great.
Thank you for the introduction. And hi, I'm Sangpyo Kim from Seoul National University. Today, I will talk about BTS and Accelerator for Bootstrappable fully homomorphic encryption. First, I will briefly introduce what homomorphic encryption is. Homomorphic encryption is an encryption scheme which enables direct computation on encrypted data without decryption. Clients on the left side encrypt and send its private data to the cloud server on the right side. And the server can perform computation without decryption. So the client get computation result without any leakage of private data because data is always encrypted. Due to these characteristics, homomorphic encryption is a key enabler of various private-sensitive applications, including private AI. Among multiple popular H schemes with different data types, we chose CKKS that uniquely support fixed point number computation as our main target. Despite such new opportunities, extremely high computational cost of H operation is a challenge. First, homomorphic encryption results in substantial ciphertext expansion. A message vector contains n over 2 data elements in its slot using the SIMD style packing. And it is encrypted into a ciphertext, which is a pair of n-degree polynomials. The coefficients of these polynomials are huge, even reaching 2000 bits. As a result, the total data size expands by more than 100 times when encrypted. Also, even the simplest operation like multiplication transforms into a sequence of complex polynomial operation when encrypted, as you can be seen here. To reduce the computational cost, two techniques are commonly used. First, the residual number system, or RNS, is used to mitigate a cost of computation between large coefficients. It converts n-degree polynomial into an L+1 by n matrix with small residual coefficients using the RNS space of primes. And second, the number theoretic transform, or NTT, is used to lower the cost of polynomial multiplication, which is equivalent to performing convolution on the coefficients. NTT can lower its cost from O(n) squared to O(n) log n. However, even with these two techniques, H operations are still very expensive. A ciphertext occupies dozens of megabytes, and H operations are dozens of thousands of times slower than plain text operations. So prior works try to accelerate H operations, which with a custom hardware, including FPGA and ASIC. However, they are restricted to somewhat simple use cases and cannot be used for complex workloads because they lack bootstrapping support. Without bootstrapping, after some multiplication, which discard the last row of a polynomial matrix in the process, we reach a state where further multiplication is no longer possible. In fact, only L multiplications are possible for an L+1 by n matrix. And so we call L the multiplicative depth of an H scheme. With bootstrapping, we can refresh the ciphertext and restore some multiplicative depths to continue operation. And we specially call H scheme which support bootstrapping as fully homomorphic encryption, or FHE. Bootstrapping is one of the most expensive H operation, which takes dominant time of application with HE. And because bootstrapping is crucial for practical workload, we designed BTS, a hardware FHE accelerator that supports bootstrapping as a first-class citizen. Let's change gear to discuss the challenges in bootstrappable homomorphic encryption and design decision for our accelerator. So what's so different when we have to consider bootstrapping? This is an example part of the bootstrapping algorithm where multiple different rotations are executed on a single ciphertext. CKKS can homomorphically rotate message vector circularly. Every homomorphic rotation and multiplication requires auxiliary data for computation called evaluation key. In fact, every different rotation requires different evaluation keys. So the usability of evaluation key and the bootstrapping algorithm is low, as you can see, and even with the compiler support, because the size of each evaluation key can reach hundreds of megabytes, on-chip storage of the accelerator cannot hold many of them. So you simply cannot avoid loading different evaluation keys from the large off-chip memory for every rotation, which is bounded by off-chip memory bandwidth. So this is our first insight in building the bootstrapping-oriented accelerator. The execution time of performance is upper bounded by the off-chip loading time of evaluation keys. Also, this means that there's no point in building a faster computation logic exceeding the evaluation key loading throughput. Now, based on this insight, we try to see what CKK's parameter sets are optimized for bootstrapping and fully homomorphic encryption. There are three tweakable parameters, N, L, and DNAM, and two criteria, amortized multi-time per slot and security level, which is decided by these three parameters. Our goal here is to find the optimized H parameter set among the best possible parameter space, as can be seen on the graph here. Now let's take a look at one by one. The first criteria is amortized multi-time per slot, which indicates the performance of a certain parameter set. And it's part of this equation reflect the performance of operation and bootstrapping frequency and operation throughput. So this is an average multiplication time for a multiplication chain, including bootstrapping divided by the number of slots. Note that the bootstrapping and multiplication time here are estimated based on the first insight that the evaluation key load time is the performance limit. The second criteria is security level. It represents the logarithmic time complexity for an attack to deduce the secret key. So higher is better, and 128-bit security level is a widely used standard these days. Now, the tweaker parameters. Here, we will not dive into the mathematical details, but only provide the trade-off in terms of criteria. First, N is the degree of polynomial. Higher N is good for security level. However, it has a mixed effect on the amortized multi-time per slot because slots gets larger, but also the evaluation key becomes larger. And the second parameter is L, the multiplicative depth. Higher L is good for amortized multi-time per slot because it means bootstrapping happens less frequently, but it is also bad for security level. Last parameter is DNAM, or decomposition number. This parameter is introduced for the first time in here in the presentation, but there are too many technical details, so please refer to the paper for the details of a DNAM. High DNAM enables more multiplicative depths with same security level, which can lead to less frequent bootstrapping. So it is good for amortized multi-time per slot. However, it also makes the evaluation key denom times larger, which is bad for amortized multi-time per slot. Now, back to the graph. Amortized multi-time per slot of various parameters set in y-axis with security level in x-axis. Denom increases along with the line of the graph. As I said before, amortized multi-time per slot is lower the better. We determine the target parameters satisfying the security level, 128-bit. And the high denom cases in the upper right of the graph have high security, but performance suffers from the large size of evaluation key, which means we have to avoid high denom for performance. And when n is 2 to the 16th, the amortized multi-time per slot deteriorates with insufficient L and fewer slots. On the other hand, the performance gain from n equal 2 to the 17th to 2 to the 18th is only 1.3 times, even though the amount of data storage required is quadrupled. Based on this analysis, we select our target as these points. So our second insight is that based on the parameter space search, only a certain set of n of 2 to the 17th, 1, 2, 3, and the matching L for 128-bit security level should be our target. then how to organize BTS that can perform an H operation within the loading time of an evaluation key. H operations are decomposed into several primitive functions, especially in low dynamic condition, like our target. New computation called base conversion is required. It changes a base used in RNS to a different base. In base conversion, a single column is used to generate a single column of a new matrix. Many prior works only focused on entity, but as denom decreases, the portion of base convergence computation increases. The below graph shows a breakdown of relative computation complexity of each function in homomorphic multiplication. As denom decreases, the portion of base conversion in total computation increases and reaches 34% in denom 1 case. So base conversion is also important in low denom condition. Based on this insight, we exploit new specialized unit for base conversion, BConv. BConv is composed of modular multiplier and modular multiplier accumulated unit, MMAU. It includes hierarchical memory structure which can maximize the reusability of data elements. And by utilizing base conversion unit, we can effectively override base conversion with other functions, including entity, despite data dependency. Now the whole picture of the P, each P contains an entity unit and a base conversion unit. And additional modular adder and multiplier for other computation and 256 kilobyte of scratchpad memory. This scratchpad is used for storing temporal data generated in H operations and prefetched evaluation keys, and also functioning as a software cache for ciphertext. We deploy 2048 processing elements in a tiled organization. And we focused on common pattern in H operation, a sequence of inverse entity and base conversion, and entity is a common pattern and appear frequently in H operation. However, data access pattern of these functions are interleaved, while entity and its inverse requires row-wise access, base conversion requires column-wise access. Interleaved data access pattern requires frequent data exchange between PEs, which is very expensive. So we require data distribution strategy tailored to this pattern to mitigate the communication cost. For this, we utilize coefficient level parallelism, or CLP. CLP evenly distributes n columns of a polynomial to PEs and compute in parallel. The degree of polynomial n is sufficiently large to obtain enough degree of parallelism. And through CLP, the necessary data exchange between PEs is limited to row-wise functions like entity. And we perform entity by mapping 3D entity to 2D array of PEs. And we connect this piece using 3 separate NOCs to enable deterministic communication, which minimize the NOC overhead. For the details of microarchitecture, please refer to the paper. For evaluation of our work, we estimated the performance, energy, and area of BTS. BTS's area 370 millimeter scale and the power 160 watt are reasonable for an HPC chip, and we simulated and measured the performance of BTS using the metric amortized multiple slot and complex workloads, including logistic regression and logistic regression training and resonant train inference and sorting. We compared BTS with other state-of-the-art implementation of CKKS, Latigo, 100X, and F1, each representing CPU, GPU, and ASIC. For a fair comparison, we also evaluated F1 Plus, which is an optimistically scaled version of F1 from 14 nanometer to 7 nanometer technology node. The below graph shows the amortized multiple slot of various implementation. BTS achieves 16 to the 2000 times better performance compared to prior works on CPU and GPU. F1 shows poor performance due to its incomplete consideration of bootstrapping. And compared to F1 Plus, BTS shows over 800 times better performance. BTS also shows better performance in the application level, achieving thousands of times of speed up in low distribution training and version 20 inference and sorting. In low distribution training, BTS also achieves 27 and 5 times better performance than GPU and ASIC implementation. To sum up, we proposed an accelerator architecture based on a legaless parameter search and observed data access pattern of H functions. We designed BTS to balance on-chip memory access, on-chip data reusability, and the competition required for bootstrapping. This is the end of my presentation. Thank you for listening.
So even though it's late, we will have. I closed it and. Okay, so we have a question.
Yeah, so Daryl Sanchez from MIT, very nice work. I wanted to ask you about, you mentioned that you find that this workload is memory bound. And can you give a little bit more insight on, because we have concurrent work, right, that we presented yesterday that shows, that you can make this problem compute bound. And so, how do you reach this conclusion? And maybe you're using smaller scratch pads, or what is the size of the total on-chip memory size? Is that the reason?
Yep. Yeah, I also heard your presentation yesterday. But in our, as I said in the example part of bootstrapping, which takes most of time in bootstrapping, it takes a major part in GPU implementation. So we think that the memory bound cannot be removed by just using enough number of on-chip memory, because every different rotation key cannot be loading of every different rotation key is mandatory to work, because we use yep.
I think I get it now. So this is because you're loading a lot of rotation keys that are
yeah.
Okay, so that bootstrapping algorithm can be decomposed, and so you can actually use a smaller set of keys.
You mean more? You use more level, and
so you can get reuse of this chunks of 4 or so.
Yeah, we by utilizing such a new algorithmic optimization, this can be possible, I think. But in case of just use a simple baseline algorithm, you cannot avoid, I mean.
Good. We have another question.
So Jaemin from Georgia Tech, the next talk. So may I have 2 questions? The first one is regarding the scheme. So I hear that you choose CKK as your overall scheme, but may I ask why you choose it over all the other, like TFAG or the other stuff, BGV, BFV?
Pardon?
Yeah, so why you choose CKKS over all the other schemes? Like,
in the case, there are many other schemes which support different data type. For example, BFV and BGV support only integer computation. So the main difference about BGV and BFV is just the different data types. So it's just an application. I think the fixed point or real number is more useful, I think, because many of the application are using the floating point, not just integer. So I just think that, and the other option is TFAG, which is scheme for binary computation, but that schema is good for non-linear function, but that the throughput of that schema is too low to use for practical application. So I just use CKK as our main target.
Yeah, thanks. My second question is, as you mentioned, the TFHE may be a little bit more friendly for non-linear. So how can you do your non-linear workload in this CKS manner?
That answer is also.
Okay, so let me repeat my question. So I see that in one of the slides you use your ResNet 20 as your
yeah.
So the ResNet 20 hash value, which is a non-linear operation. So how can you deal with this in your work?
Many of the non-linear functions are replaced by the approximated high-degree polynomial. So many of these can be replaced with them.
Okay, thanks for staying with us. I think we will conclude this great session, and thank you and enjoy the excursion. Bye-bye.